Welcome back, engineers. In this video, let's talk about clocks and see how they can impact our distributed systems and transactions. I hope you're ready. Let's get started. So clocks are such a fascinating thing. You would imagine that of all the things that could go wrong in a distributed system, the simplest of things are clocks, and they should be so reliable because they just have one thing to do, to just maintain track of time and tell us what time it is, right? But as you look at it closely, you will realize that they're not as reliable as you think. So let's see the type of clocks that we have and see why they are an issue and what are the possible solutions, right? So first, let's talk about the types of clocks that are currently available. So first one is a physical clock, which is made of quartz crystal, right? So this is part of the analog watches in our wall clock, and also the clocks that come with computers and laptops, which display time even when they are offline, right? So this is how they work. So there is a quartz crystal inside the clock, and there is a battery which is sending an electric current which is oscillating the quartz, right? And because of these oscillations, we are able to capture the number of times it is oscillating using a microprocessor. This is where the logic is happening, and using some kind of a magnet, we are able to spin some motors which are in turn spinning the gears, and we are able to see our seconds hand, minutes hand, and hours hand move, right? So this is a simple oscillator, and it's been there since the longest of time, right? And then there is the atomic clock. Atomic clock use the similar concept, but instead of oscillating a material like a quartz crystal, they are oscillating the atoms like cesium atom, right? Using electromagnetic radiation, we are able to oscillate them or make them vibrate many number of times so that it is having more accuracy in terms of time, right? So this is the atomic clock. So just to give some perspective, the quartz oscillator oscillates about 32,000 times per second, whereas the atomic clock oscillates at about 9 to 10 billion times per second. So the more the number of oscillations, more is the accuracy of the clock, right? And because of this, atomic clocks are quite useful when it comes to measuring time very accurately. So while the physical clocks use the quartz crystal method, they are reliable for everyday usage. We need more accuracy in terms of computing systems, and especially for distributed systems, this is where we can make use of atomic clocks. So these atomic clocks are part of the global positioning systems, which are satellites hovering all over the earth, giving us more information, and they make use of these atomic clocks. And whenever we talk about UTC time, the universally coordinated time, this is simply the weighted average of many atomic clocks around the world, and they keep in sync with each other to make sure that we have the best of accuracy, right? So these are the two types of clocks that are available. Now let's see a couple of ways of looking at time, especially from a software engineering point of view, right? So there are two ways of looking at it. One way is to look at it in a duration, other in point in time. So there are some examples. Let's have a look. So the first four questions, if you look at it, has this request timed out yet? What's the 99th percentile response time? How many queries per second did the service handle on average in the last 5 minutes? How long did the user spend on our website? So all these questions involve a duration. There is some kind of a start time, and there is potential end time which is being tracked. Request timeout, which means that there is an initial start point where the request has been initiated, and maybe at 60 seconds it will time out. So there is a duration, right? Similarly, the other questions. And the bottom four are about point in time. If you look at it, when was the article published? At what date and time should the reminder email be sent? When does this cache expire? What is the timestamp on the error message in the log file? All these are point in time, right? They are a precise point in time which represents certain event occurring. So the article was published at exactly 10 a.m. on 25th May 2025, and so on, right? So these are the two ways of looking at time when it comes to software engineering. Now let's discuss the problems with clocks, especially when it comes to distributed transactions, right? So the first problem is clock drifts. So because of the nature of these clocks, the analog clocks which are using the quartz crystal, the oscillation changes. It's not so accurate every second. It can change due to temperature. It can change because of the angle at which the clock is maintained. It can also change when there is some strong presence of magnets around it and so on, right? So there can be many factors affecting this, and because of this, the oscillation can either slow down or it can pace up, which gives us different movements in the gears, which in turn gives us different time, right? So this phenomenon is called a drift. So this phenomenon is called a clock drift, right? And drifts are possible in atomic clocks as well, but they are very, very minute. So to understand these drifts in a better way, let's look at this paragraph. The quartz clock in the computer is not very accurate. It drifts, runs faster or slower than it should. Clock drifts vary depending on the temperature of the machine. Google assumes a clock drift of 220 parts per million for its servers, which is equivalent to 6 millisecond drift for a clock that is resynchronized every 30 seconds, or 17-second drift for a clock that is resynchronized once a day. So if there is a machine that is getting synchronized with some network to update itself about what is the current time, there would still be a 6 millisecond drift if it is synchronizing every 30 seconds, and if it is synchronizing once a day, there is still a 17-second drift for that machine. So because of these drifts, we don't always expect to see the latest updated time, right? And because of the fact that clocks do drift, almost all systems provide a mechanism to keep updating those clocks through some network server, which is in turn updating itself using some atomic clocks or distributed system somewhere to keep itself updated, right? So for example, if I am on this Mac and this Mac is using some quartz crystal inside, but I want to keep it synced with using some network, so I go to date and time settings and I check this box, set date and time automatically, which is using this server time.apple.com or time.google.com or time.microsoft.com or whatever, and it is keeping itself in sync. So this is not using the local watch that is available here, but it is constantly checking periodically to update itself using this server, right? So because of this, so this is a network call again. Because of this, there could be network latency, and one sync can be faster, other sync can be slower, and because of these we can have latency issues in clocks. And there could also be issues about skipped updates. Some updates may not ever happen, and because of this there can be misbehavior in terms of clocks, and we can notice this if we look at our logs. Sometimes there could be scenarios where our clock has moved ahead and the network time is still falling behind, and in the next sync we got to know that we need to roll back our time, and in the meanwhile if there are any updates happening, we will see time is actually moving backward when we look at the timestamps, right? So these kind of issues happen when it comes to clock synchronization, right? Now let's look at why is this a problem in distributed systems. Let me see if I can close this. So let's take this example to understand why this drift is creating such an issue. So let's say we have 3 nodes, and let's say we are in a multi-leader system, right? And we have node 1, node 2, node 3 potentially operating at different local times, right? So node 1 is at 42003. So inside the clock of node 1, we have timestamp 42003, right? And there is some client coming in giving some instruction, set value x to a, x to 1, and we are pushing this update to node 1. Node 1 is receiving response at 42004 that the update is successful, right? So because of the replicating nature of the multi-leader system, we are passing along the updates to node 3 and node 2 from node 1, right? Now let's look at node 3. So node 3 is currently at 42001, which is slightly drifted apart, or there is some deviation of plus or minus 2 milliseconds. So in this case, node 3 is falling behind node 1 by 2 milliseconds. We don't know which is the accurate time, but we just know that there is some deviation. Let's see if this will cause an issue. So from node 3's point of view, at 42001 nothing happened. At 42002 it received an update from node 1 saying, hey, set x to 1 at this timestamp, right? So it has updated itself to 1, and then client B is calling upon an increment operation on the same thing. So at 42003 it has incremented itself, now the value of x equal to 2 with timestamp of 42003 from this node's perspective, right? And again, because of the replicated nature, this update is going to node 1 and node 2. But the update from node 1 has not reached node 2 yet. So from node 2's point of view, this update has reached first. 42003 has reached first, followed by 42004, right? And because of this, there is an issue here. It is showing that first you set x to 2, and then we are receiving this update, you set x to 1. So the final update from node 2's point of view will be 1, which will bring us to an inconsistent state, and this update is lost. Just because of the drift in the local clocks, this issue has happened. And because of this, the write by client B is usually later than the write by client A, but B has an earlier timestamp. Because of this, there is misbehavior in the system, right? There can be many issues like this when it comes to dealing with timestamps, and many of them go unnoticed. They are silently logged, they are silently updated, and many of them go unnoticed, right? So that is a major problem with clocks when it comes to distributed systems. So what are some solutions? Don't use timestamps. Use logical approaches for handling distributed systems. So for example, use Lamport clause, which talks about every event getting a number. So every event gets some kind of unique identifier, which is automatically incrementing and so on. This is not relying on any particular timestamp. It is relying on some global total ordering, right? So this is one way to do it for ensuring ordering, but this does not guarantee any causality, which means that if 2 needs to happen before 1, this system does not take care of that. And we have seen another system in CRDT, which is using vector versioning, also known as vector clocks, where we are ensuring causality across different nodes. We already saw how CRDT works, and we took examples and did a dry run using a timeline using CRDT's algorithm, right? So definitely check out that video if you haven't watched it already. So this is how we can ensure causality plus ordering. If you do need to use a timestamp, then go for confidence intervals instead of absolute time. So here in our example, we were using absolute time, right? 42003, 42001, and we were blindly using these timestamps for making our updates. But instead of that, use confidence intervals. So this system is also used in TrueTime by Google, and it is used in Google Spanner. So by exposing an API, TrueTime API, we can actually make a call to TrueTime server and ask, hey TT, what is the timestamp now? And it will return not the accurate timestamp right now, but it will return a range, earliest to latest, with some confidence interval. So there is some timestamp, let's say 1010, with an interval difference of plus or minus 5 milliseconds. So the time could be 10.05 to 10.15. Somewhere in this range is the time. Instead of giving an accurate time like this, it will give some kind of a range like this. So let's try to understand how this confidence intervals work using an example. So let's say we have two nodes, node A and B, and time is starting from left to right, and currently we are in node A, where the current time is 1000. So we are measuring time in milliseconds in this case, and we are at 1000. And the transaction 1 starts here. At this point of time, A is asking the TrueTime server, hey, what is the timestamp now? The TrueTime server, instead of responding with the current timestamp, it will respond with an interval range, which is saying that it is somewhere between 1005 plus or minus 5 milliseconds, which means 1000 to 1010. So this could be the range. So current time is somewhere in between this range. So now node A is confused. Should I use 1000? Should I use 1005 or 1010? So in order to avoid any confusion, it will decide to wait until 1010. So it will wait until the local time crosses 1010, just to be sure that this interval range is not violated. So once the timestamp has crossed 1010, it will commit at a later point of time, maybe at 1011. So this is how confidence intervals are used in TrueTime. So let's say there is another transaction coming in during this operation. So let's say it's coming in from node B. Maybe there is some synchronization happening with transaction 2. So again, at this point of time, we ask the TrueTime server, hey, what is the timestamp now? It will respond by saying the timestamp is 1010 plus or minus 5 milliseconds. So it could be somewhere in between 1005 and 1015. which is overlapping with this one, right? The 1000 to 1010. Let's say this whole thing is happening during this operation, right? So just to be sure, and just to be sure that B has not happened before A, we will wait out the duration 1005 to 1015. So once 1015 is crossed, we will commit this transaction at 1016. So that is how we can ensure causality as well as ordering, right? So that is how confidence intervals work. So having said all that, the modern systems use a hybrid approach. They use a concept of network clocks plus atomic clocks plus confidence intervals to make sure that we have the best of accuracy in time, right? So we don't normally see these issues with clocks in our day-to-day usage, but it's good to know about these topics and when we are discussing system design with time-sensitive applications, right? So maybe you are building an application that is very time sensitive, like a stock market application that requires you to be accurate to the ticker prices at the millisecond level or microsecond level. We need to be aware of these clock drifts and make sure that the price data is not altering because of these drifts and so on, right? So that's all for this video, guys. Thank you so much for watching. I will leave some documentation about TrueTime and Spanner for you to check out in the description, so definitely check it out. And also some documentation about how atomic clocks work. You can also check out this Encyclopedia Britannica. I will leave the link in the description. So if you have any doubts, definitely put them in the comment below. Do leave a like if you found this helpful. Do subscribe if you haven't done already so that you don't miss out on any future videos. Thank you so much for watching. I will see you in the next one. Cheers.